So if you had a chance to think about this and you had some clear mind, and you were going to guess, you would guess probably that other compounds besides benzene can be aromatic. As a matter of fact, we can have different numbers of carbons in the aromatic ring, or we can have other different atoms, which we frequently call heteroatoms, in the ring itself. So let's look at these other compounds. Aromatic compounds fulfill two criteria, and Klein suggests this is two criteria, but this first one, as we've seen, is really kind of three criteria, right? It's a fully conjugated ring with overlapping p orbitals. Okay, and that means that we have a ring full of essentially sp2 hybridized carbons. It would be possible to have an sp3 hybridized carbon in there too, but that would be difficult. Mostly it's going to be sp2, I think, with no exceptions. All right, and the second one is it has to meet Hückel's rule, and that is that the number of, where are we here, pi electron pairs has to be an odd number, right? Or you have to have 4n plus 2 pi electrons. These are the same thing. All right, so Klein says two criteria. I'm suggesting there's sort of four things in here. All right, that's an aromatic compound. Now an anti-aromatic compound fulfills exactly the same criteria, except it has a different number of pi electrons. It's 4n instead of 4n plus 2. Okay, now the systems we're going to look at, are mostly going to have, 2, 6, 10 pi electrons. And here, not 2 or 6 or 10 electrons, right? 14, of course. Can you see this goes up by 4, right? 18. But for the most part, they're going to be basically in this world right here, 2, 6, or 10. And that's because they fit this rule right here. All right, so let's go on. We've already looked at these before, these rules before, so let's move on. Annulenes are rings that are fully conjugated. So here's an annulene. It's fully conjugated, right? You see that it's double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond, double bond, right? It's fully conjugated. Double bond, single bond, double bond, single bond, double bond, single bond, double bond, right? Fully conjugated. Same thing over here. Okay. Now that we have looked at that, now that we've defined the term annulenes, we see that some are aromatic while some are anti-aromatic. Why is that? Well, it's because they are fully conjugated ring systems, overlapping p orbitals, atomic orbitals, right, to make pi molecular orbitals, right? Annulene is neither aromatic nor anti-aromatic. Why? Okay, you're going to be tempted to Google that without thinking about it, and I hope you'll try to give it a shot first. Let me give you a hint. You'll learn this better if you think about it first. Hint: draw all atoms. Draw all the atoms. Lost my marker here, just a minute here. Draw all the atoms. Okay, that's your hint. All right, now you need to go practice with conceptual checkpoint 18.10. Okay. All right, now some rings, in order to fulfill the aromaticity requirements, they're going to have a formal charge. So look at a 5-membered ring, for example. We'll draw this extensively in the next couple pages, I think, but a 5-membered ring. Well, if this is sp2, and this is sp2, and this is sp2, and this is sp2, and this is sp2, right? And if I'm going to have 2, 6, or 10 pi electrons, right? Then I'm going to have 2, 4. That's a lone pair of electrons there. Sorry for the ugly pair. There's a lone pair of electrons right there. That's going to have to be minus, right, in order for this to be aromatic, right? Because I got 6 electrons in there. In order for there to be only 2, well, I'd have to have lots of pluses on here, which would, you know, technically work, but you don't want to have that many charges in one small place. Okay, so if 6 pi electrons are present, 2, 4, 6, which is exactly the same number I got by doing this, right? 2, 4, 6. Draw the resonance contributors for the structure. So draw this guy out and draw the resonance contributors. Stop the video now and practice that. Okay, let me suppose that you did. I'm going to draw here. Right, so one resonance contributor is there. Here's another one. So I do a new double bond there, new double bond here, or that's the same double bond there. There's my minus, right? You see what's going on? And these then can come here, right? So draw that out. If you hadn't drawn that yet, draw the one out which I did not draw here, right? I left blank. I implied it by showing those electron pushing arrows. Okay, so the cyclopentadiene, the pKa, is much lower than the typical CH bond. Why? Why is that? Well, so here's cyclopentadiene, right? If you take a proton off of there, what happens? First of all, you get water, right? But draw out this other guy that you get. What do you get? Right? That's what you get when you abstract that proton off of here. Okay? Now you remember that HA, the acid, is in equilibrium with H plus and A minus. The strength of this base is always mapped over to the stability of that conjugate base. So if this is super stable, that's going to be a better acid, right? And look at that. Wow, 16. Oh my goodness. I mean, wow. This is a log scale, right? So this acid, this carbon-hydrogen bond right here, is billions of billions of billions times more acidic than that carbon-hydrogen bond. Wow. Folks, I'm not being dramatic. You've got to stop and look at that. This carbon-hydrogen bond is 1 times 10 to the 34 times more acidic. What? Right? Because this is P scale. Incredible. Do you see what aromaticity means? Big deal. Big deal. This is why it's so important in nature. Okay? All right. So let's look more. Now, consider a 7-membered ring. Now, if you have a 7-membered ring, then in order to use Frost's circle, which we learned in last presentation, Frost's, I suppose that says circle. I'm struggling spelling today. Frost's circle. In order for you to have 6 pi electrons in these 3 bonding molecular orbitals, right? Boom, 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 boom. 1, 2, 3, 4. Well, I don't know if I've got that right. There's 7, right? 1, 2, 3, 4, 5, 6, 7. That's right. Okay. Now consider what this means. Let's put 2 pi electrons here, 2 pi electrons here, and 2 pi electrons here. They've got to go alternating because it's fully conjugated, right? This then has got to be a carbocation, right? Because it has to have an unhybridized p orbital. You knew already from our last chapter that this was conjugated, right? You have an unhybridized p orbital here, an unhybridized p orbital here, an unhybridized p orbital here. Side-to-side overlap, which I implied by that double bond, right? But if this is an empty unhybridized p orbital, watch this. Empty unhybridized p orbital, you can still get side-to-side overlap. And that's why allylic carbocations, crud, sorry about that, are stable. They're resonance stabilized. My handwriting is horrible today. Wow, I'm really sorry. So an allylic carbocation is resonance stabilized because of this. Okay, that was that's something that you want to go. If that doesn't make sense, you really want to go back and look at that, because that's what we're doing here. So can you see? This is not just allylic. That's allylic on both sides, right? Double bond, carbocation. Double bond, carbocation. Okay, this is going to easily go over here. In which case, this will easily go over here. In which case, this will easily go over here, right? So this is, where's mine? Awesome. Okay. If 6 pi electrons are present, what charge will be necessary? Which we just answered that. Draw the resonance contributors for the structure. You need to stop and do that. Practice with Skill Builder 18.2, and then move on to the next slide. Okay, now let's consider rings that have heteroatoms in them, and this heteroatom that we're interested in right now is nitrogen. Okay, if you have nitrogen, you know now nitrogen has a tendency, if it has no formal charge, to take 3 bonds in a lone pair of electrons, right? So, do you see a lone pair of electrons here? Okay. You see a lone pair of electrons here. All right. So, how many pi electrons in this system? Aha. If you let nitrogen be sp2, it is sp2 hybridized, then you've got an unhybridized p orbital here. There's my unhybridized p orbital on nitrogen because it's sp2 hybridized. Then if you let that be the case, then the lone pair of electrons is going to be out to the side. It's going to be pointing out, not in the plane of the ring. So it turns out there's 6 pi electrons here, right? 2, 4, 6. 2, 4, 6. Okay. Over here, this hydrogen is pointing out, right? Because this is also sp. Well, you can't tell it's sp2 by looking at it, right? It looks like it's sp3 because it's got 3 single bonds and a lone pair. However, and this is a big deal now. This is the point of the slide, really. Okay. However, this lone pair. Watch this. If allowed into a p orbital, unhybridized p orbital, will add to the pi electrons. Okay, so I've got 2 pi electrons here, 4 pi electrons here. If I can make these into, if I can force these into a p orbital, then the whole thing gains aromaticity. That's really subtle. Boy, I pause right there because it's so subtle. Look at that. Now, if I can make this sp2 hybridized, then this whole thing will be aromatic. Let me go back and say something here, and I'm doing this without visual cues. I'm doing it without notes on the slide. Listen to what I'm saying. Do you know why something goes from sp3 to sp2? Why does that happen? Why does that happen? Why does anything hybridize in the first place? Because there's an energetic benefit. Okay? Because it's more favorable energetically. It's more stable. It's lower potential energy. Why does a book fall down and not just stand on its edge? Because it's energetically favorable. It's more stable, right? Okay. So if you gain stability by aromaticity, then there's no longer any reason to go sp3 if it can go sp2. That's very subtle, very, very subtle. There's no way I would have gotten that when I was where you guys are. Okay, but you have learned that, right? So I'm just appealing to something you learned in Principles 2, and we went back to in Organic 1. All right. So anyway, the conclusion is that this lone pair of electrons here are, where am I here? This lone pair of electrons right here, they are in the pi system. So there are 6 pi electrons here. also. All right. Wiley does, Klein does a good job in the book at explaining this. And of course, I'll discuss it with you in class as well. I need to move on. Okay. This is what I just said a minute ago. If the heteroatom's lone pair is necessary, it will be included in the Hückel number of pi electrons. So this lone pair here is not necessary, right? You've got your 2, 4, 6 pi electrons. 6 pi electrons. Over here, it is necessary to gain aromaticity. 2, 4, 6. So it will go into the system. Over here it does not. Over here it does. Okay. We've said it a couple different times. I think these pictures are helpful. I used those a little bit, I guess, but all right. Now, if the lone pair is necessary to make it aromatic, the electrons will not be as basic. So you know that that nitrogens are basic, right? The lone pair of nitrogens are basic. That's why it's a base. Ammonia is a base, right? So here's the base action of a nitrogen. All right, and so you have over here pyridine. This is called pyridine. Watch this, This is the pyridinium cation. All right. Now, how acidic is this? 5.2. Why? Well, that's about how acidic nitrogen, ammonium ions are. Okay, but look over here. If you use this lone pair of electrons as a base, then this becomes the pyrrolinium. Doesn't matter what it's called, okay? This is the pyrrolinium cation. Is this aromatic? No, right? Because those pi electrons here, these were pi electrons. Now they're used as a bonding electrons. They're no longer pi electrons. So since it's not aromatic anymore, this acid's really good. That's as good as HCl. Right? Wow. Why is it such a good acid? Well, because there's such a big difference between the stability of pyrrolinium and pyrrole. I don't really care about these names, okay? I'm only using them because it's an extra color for you, okay? So you should say it out loud. You'll be more comfortable with this if you write it out and say it. This is pyrrole. This is pyridine, okay? So look at that. This is a really strong acid. Why? Well, because when it gives up that proton, it gains aromaticity. Aromatic? Yes. Man, my writing is horrible today. I always say that, don't I? Making excuses. All right. All right. So, now another way we can consider this is by looking at the electrostatic potential maps. Now you have to have an electrostatic potential map. Of course, you can't generate one of these in a quiz or exam. But if I gave you an electrostatic potential map, you would look at this and you would say, oh wow, there's a hot spot right there. See a hot spot for electrons? It's red. Wow, that's a sore spot, right? But where's the hot spot over here? Oh, it's spread all over. Can you see that? So we don't have a big hot spot right here. Can you see that? That means those electrons are spread around. Wow, I'm so dizzy. I'm so dizzy. Around and around and around. Pi electrons. Aromatic. Love it. Love it with me, please. Okay, now go practice with Skill Builder 18.3. What page is that? I'm looking at my book. You are too. I know you are. You should be. Better be looking in your book. 18.3. Skill Builder. This is on page 850. Okay, so hopefully you practice with that. All right, practice with this one too. Pause the video and give answers for this and give reasons why. If you're not comfortable with the aromaticity, you need to have the rules out in front of you. There's no reason to have these memorized yet. Right? You have to have them memorized for the quiz and for the exam. But while you're memorizing them, you should have them in front of you and check them off. Are these aromatic, antiaromatic, or non-aromatic? Okay, I'm going to suppose you paused the video. If you didn't, do it now. Pause the video and do these and work out notes on these. Okay, so let's look at these. So is this aromatic, anti-aromatic, or non-aromatic? Well, the fact that there's a nitrogen in here has nothing to do with it, okay? Nothing to do with it. So don't even say, well, no, it's not aromatic because it has nitrogen. You can't say that. And we can't say it's aromatic because it's got alternating double bonds. Is it planar? In other words, are they overlapping p orbitals? Are they all parallel? Yes. Is it cyclic? Is it a ring? Yes. Is it fully conjugated? Yes. Is it a Hückel number of pi electrons? Well, we need to know if these are in the system then, right? Well, they can't be because they're pointing out, right? If this is trigonoplanar, these are pointing out, right? So this cannot be in the system, pi system. So there are 8 pi electrons. Hückel number? No. This is anti-aromatic because it fulfills these 3, but not that one. So this is anti. Okay. Now what about this one? Is this aromatic, anti-aromatic, or non-aromatic? Well, these electrons would be pulled into the pi system if it gave me a Hückel number. But I have 2, 4, 6, and that would be 8. So no, these are not pulled in the system. This is sp3. It is not fully conjugated. How do you spell fully? It's not fully conjugated? No, it is non-aromatic. Okay, what about this one? 2, 4, 6, 8. Who do we appreciate? 10 pi electrons. It's cyclic. In other words, it's a ring. Yes. It's fully conjugated. Oh man, sorry. Fully conjugated, yes. It's planar. In other words, the unhybridized p orbitals are all parallel or overlapping. Yes. And it's a Hückel number. Yes. This is aromatic. Okay, so this was non-aromatic, this was anti-aromatic, and this is aromatic. All right, now let's look at this one. 2, 4, 6, 8 pi electrons. This is going to be anti-aromatic. Right, go through and ask yourself the questions. Is it planar? Is it cyclic? Is it fully conjugated? And is it a Hückel number? And the answers to the 3 of those is yes. The last one is no. It is not aromatic. All right. Okay, so the last thing slide I want to look at is this. Many polycyclic compounds are also aromatic. You have naphthalene, which you should say out loud. Anthracene, draw it and say it out loud. These 2 are pretty common in textbooks and such. Okay, you'll be more comfortable if you say these out loud and draw them. And then phenanthrene, which we don't see as much. If you've got the energy for it, draw it. Okay. These compounds are aromatic. Why? Well, go through the 4 criteria, which Klein calls 2. Go through the 4 criteria and demonstrate to yourself that they satisfy all 4 criteria. Now, such compounds can also be shown to be aromatic using heats of hydrogenation. So what I want you to do, this is the last exercise for this video, is to design an experiment. Design an experiment. All right? In other words, just say what you're going to do, right? And of course, the key is right there. Say what you're going to do to show that those are aromatic. It's very much like what we did in the beginning of this chapter. Okay, I hope aromaticity is becoming familiar to you as we're doing this. Best wishes.